Okay. Today's topic, today's topic is what is space density from medium ontology to the space-time constant key. This is actually the second talk. The first was on December 20th last year. Today, I want to discuss that a simple but foundational question about space-time. Last time, I suggested space-time may possess an intrinsic density-like property, and the density is not matter, not vacuum energy, and not a source of gravity. So today's goal is to clarify what this density means physically and how it connects to Zhang Xiangqian's unified field theory. And also, I will explain why this perspective may help us think differently about gravitational anomalies, often attributed to dark matter. In modern physics, space-time is not passive. It curves, it carries waves, and it governs motion. But we rarely ask a basic question: what is space-time physically? This talk explores the possibility that space-time itself has intrinsic physical properties, in particular, a density-like property that may already be encoded in the constants of nature. So for the next several slides, slide 2 to slide 5, I will review what we have discussed in last talk, since it's been almost 3. Why it doesn't show? From slide 2 to slide 5 will be a review of last talk, so that for people who do not remember or who didn't attend the first talk, will have basic idea. So if space-time acts physically, shouldn't it have intrinsic physical properties? In general relativity, space-time curves and influences motion, but it is still often treated as physically empty. In quantum field theory, space-time hosts quantum fields, yet the physical nature of space-time itself is rarely specified. So the issue here is not a mathematical problem. It is a conceptual gap. We use space-time actively in physics, but we rarely ask what space-time actually is. Slide 3. Space-time acts, but what is it? We know that space-time affects many physical processes. It influences motion, governs the propagation of waves, and determines gravitational behavior. Yet, despite these roles, we rarely describe space-time as a physical entity with intrinsic properties. This conceptual ambiguity becomes particularly visible when we try to explain large-scale gravitational phenomena, such as galactic rotation curves. In many discussions, the assumption is something must be missing in the matter content. But another possibility is that our understanding of space-time itself may be incomplete. Slide 4. Two conceptual responses to dark matter. When physics encounters phenomena like galactic rotation curves, there are two broad ways to respond. The first approach is a mainstream one. We introduce unseen matter, usually called dark matter particles. The second possibility is to reconsider the physical properties of space-time itself. Perhaps space-time is not simply a geometric stage, but has intrinsic properties that become dynamically important at large scales. This talk explores the second possibility. Slide 5. Enter unified field theory. Zhang Jiangqian's unified field theory begins from a very different premise. In his framework, space-time is not a passive background. Instead, space-time is treated as a real dynamical medium. Fields arise from the geometry and motion of space-time itself. Later work by Zhuben Jiang has shown that space-time motion can even be derived from standard physical principles. So, if space-time moves and behaves like a medium, a natural question arises: what physical properties must this medium possess? For all the referenced paper, I have links on the last slide. Slide 6. My aim in this paper. This paper has three main goals. First, I introduce the idea of an intrinsic space density at the ontological level, meaning at the level of what space physically is. Second, I explain why such a density cannot appear directly in field equations. Third, I show how this density is represented in unified field theory through a geometric constant called chi. Slide 7. What does space as a medium mean? If we say that space behaves like a medium, what does that mean? A medium typically has several properties. It can carry waves. It can store action or energy. And it can resist deformation. In ordinary physics, anything that resists deformation usually has some form of density. So, if space-time behaves like a physical medium, it is natural to ask whether it also possesses an intrinsic density-like property. Slide 8. Defining space density. In this work, I define space density as an intrinsic density scale of space itself. This density does not describe matter in space. It does not describe vacuum energy, and it does not act as a gravitational source. Instead, It is a background property of space itself, independent of whatever matter or fields may exist within it. Slide 9. What space density is not? It is not particles. It is not the quantum vacuum. It is not dark energy. And it is not a source of gravity. Instead, it is simply a property of space itself as a physical medium. Slide 10. Scalar nature of space density. In last talk, a person asked the question, if the density is a scalar or vector. I didn't have a direct answer, although Terry answered, says it should be a scalar. Yeah, it is a scalar. It doesn't have direction. It has a magnitude similar to ordinary density in a fluid. Any directional behavior we observe in physical phenomena arises from motion, geometry, or boundary conditions, not from the density itself. Slide 11. Ontological summary. At this stage, space density answers a single fundamental question: what is space physically? At the ontological level, this density describes the intrinsic nature of space. However, it does not yet describe dynamics or equations of motion. Those belong to a different level of description. Slide 12. Why it cannot appear in field equations. Here we need to distinguish two different concepts. Ontology concerns what something is, its substance, and the intrinsic properties. Dynamics concerns how something behaves, its response, and evolution. Field equations describe dynamical behavior, not substance. Therefore, an ontological property like space density cannot simply be inserted directly into field equations. It must first be translated into a geometric or dynamical form. Slide 13. Need for a geometric representation. For space density to influence space-time dynamics, it must be encoded in a geometric constant. In unified field theory, this geometric constant already exists. It is called key. Key is not the density itself. Instead, it is the geometric representation of that density within space-time dynamics. Slide 14. Introducing key in unified field theory. In John's unified field theory, key is called the space-time background inertia intensity constant. This constant is already part of the theory. I'm not proposing a new constant. Instead, my goal is to clarify its physical interpretation. Key regulates how strongly space-time resists deformation. Slide 15. Bridge to standard physics. An important feature of key is that it connects directly to familiar physical constants. In unified field theory, key is related to the speed of light and the gravitational constant, by K equals C cubed divided by G. This relation helps bridge unified field theory with standard physics. Dimensionally, K has units of mass per time, representing the intensity of spacetime's inertial response. The paper about constant P in Huang Bingjiang's paper, the link to that paper is also on the last slide. It should explain why K equals C cubed divided by G. Slide 16, important distinction. It is essential to distinguish between space density and K. Space density describes what space is. K describes how spacetime responds dynamically. So they exist at two different levels of description. They are related, but they are not identical. Slide 17, space density scale. Now we can connect the concept of space density to familiar physical constants. In this framework, the intrinsic density of space is related to the geometric constant K through the relation. We use mu s represent space density. It equals K squared divided by h bar times c. In unified field theory, K itself is related to known constants through K equals C cubed divided by G. If we substitute this relation into the density formula, we obtain mu s equals C to the fifth divided by h bar G squared. This is exactly the same expression as the Planck density scale. The important point is not the numerical value, but the interpretation. In conventional physics, the Planck density appears as a derived scale constructed from fundamental constants. In this framework, the same scale is interpreted as the intrinsic density of space itself. So, this work does not introduce a new scale. It reinterprets an existing fundamental scale. What this work proposes is a different interpretation. Instead of viewing Planck density purely as a quantum gravity limit, we interpret it as reflecting the intrinsic density of the spacetime medium itself. In this picture, the Planck density is not merely a derived combination of constants, but the natural density scale associated with spacetime's intrinsic structure. So, one may ask, if space has Planck density, why don't we see huge gravitational effects everywhere? Because space density is not a gravitational source term. It characterizes the intrinsic inertia of the spacetime medium, not matter density. Gravitational effects arise from how matter interacts with spacetime geometry, which is governed by G. So what is is the observational test of this idea. One possible place to look is large-scale gravitational systems, such as rotating galaxies, where space-time response may accumulate over large spatial scales. This is why the framework may offer an alternative interpretation of dark matter-like phenomena. Slide 18, conceptual correction. Earlier interpretations tended to treat density as derived from key. My interpretation reverses that direction. Instead, space possesses intrinsic density first. Key then appears as a geometric representation of that density within spacetime dynamics. Slide 19. 3 levels of description. This slide summarizes the conceptual structure proposed in this work. At the deepest level is the intrinsic property of space itself, which I denote as a space density. This describes what space is as a physical medium. When space-time dynamics are expressed geometrically, this intrinsic property appears through the constant key. In unified field theory, key represents the inertial intensity or rigidity of space-time. Finally, when matter interacts with space-time geometry, the coupling strength is described by the gravitational constant G. So, the 3 constants correspond to 3 levels of description: the ontology of space, the geometry of space-time dynamics, and the gravitational interaction between matter and space-time. Slide 20. What appears in field equations? In field equations, the quantity that appears explicitly is key, not the space density itself. The density is always present implicitly, but its dynamic influence is carried through key. Slide 21. What does key do physically? Physically, the constant key characterizes the intrinsic rigidity of space-time. It measures how strongly space-time resists deformation when it is dynamically excited. It is important to emphasize that key itself is a universal constant. It does not vary from place to place. However, the observable effects associated with key can become more or less visible depending on the physical system. In small or local systems, such as planetary systems or laboratory experiments, space-time response is mostly local, and the influence of key remains effectively hidden. In large coherent systems, such as rotating galaxies, space-time response can accumulate over very large spatial scales. In those situations, the intrinsic rigidity of space-time becomes dynamically significant, which can appear observationally as additional gravitational effects. Slide 22. Local versus global behavior. In local systems, planets, laboratories, or stellar neighborhoods, space-time response is mostly local. In these regimes, Newtonian gravity and general relativity work extremely well. But in large-scale systems, like rotating galaxies, space-time response can accumulate over large distances. In such systems, the effects associated with key may become dynamically visible. Slide 23. Galaxies and large scales. Large rotating systems like galaxies involve coherent motion over enormous spatial scales. These systems may engage spacetime's global rigidity. The cumulative response of spacetime could then appear as an additional gravitational effect. Slide 24. Reinterpreting dark matter. This perspective leads to an interesting possibility regarding dark matter. In the conventional interpretation, discrepancies such as galactic rotation curves are explained by introducing additional unseen matter, dark matter particles. This framework discussed here suggests another possibility. If spacetime possesses intrinsic rigidity characterized by the constant key, then in very large and coherent systems, the cumulative response of spacetime itself could become dynamically important. In such cases, spacetime may generate additional effective gravitational response without requiring additional matter. Observationally, this could appear as the presence of actual gravitational mass. In other words, what we interpret as dark matter might instead reflect how space-time itself responds on very large scales. This interpretation does not require new particles. It suggests the same space-time behaves differently depending on the scale and structure of the system. I want to emphasize that this talk is proposing a conceptual framework, not claiming that dark matter is definitely explained by this mechanism. I just feel that this work explains dark matter more reasonable than unseen matter. Slide 25. Why general relativity still works. General relativity remains an excellent theory. It works extremely well in regimes where space-time effects are local and weak. In this view, general relativity emerges as a local approximation of a deeper space-time dynamics. Slide 26. Relationship to John's unified field theory. My work fully accepts the framework of unified field theory. I'm not modifying its equations. Instead, I'm clarifying the physical meaning of the constant key within that framework. Slide 27, relationship to Huang Binggang. Huang Binggang developed that Young's unified field theory mathematically. He actually has published over 10 papers to what's the word for that? Yeah, he has built a complete system of new physics from that unified field theory premise. His paper also, the link to his paper is also on the last slide. His work treats space density mainly at the field response level. My contribution as a deeper ontological interpretation. I think these two perspectives operate at different descriptive levels and can coexist. That the scale, the formula for mu, actually from my discussion with Huang. So next, slide 28, unique contribution. My contribution of this work lies three areas. First, proposing an ontology of space as a physical medium. Second, clarifying the hierarchy of constants. It is a space density, and then K, and then G. Third, building a conceptual bridge between unified field theory and mainstream physics. Final takeaway. The overall picture can be summarized in three levels. At the ontological level, space density describes what space is. At the geometric level, K determines how spacetime responds. At the gravitational level, G determines how matter couples to spacetime. Yeah, last slide. If spacetime is real and active, then it must possess intrinsic physical properties. Unified field theory already treats spacetime in this way. So I'm looking forward to your questions and discussion. Those are the links to the relevant papers.
Someone requests you to paste a link to the chat, or maybe you can.
Yeah, I can do that. Okay, that should be simple.
Maybe you can send me the slides so that I can forward.
Oh yes, I will send to you right after the talk. Yes.
So I got a question on YouTube. How about the electric universe theory?
Unified field theory, are you asking?
It's asking on YouTube. How about electric universe
Electric.
theory?
I have not heard of electric field theory. What is it?
This person's on YouTube, but
Oh,
never mind.
yeah, I have not heard of electric field theory. Sorry.
There's another question from Ron. Is space density mutes a constant?
Oh, yeah, space density is a constant.
And there's another question: is the galactic scale effect on rotation curves like frame dragging?
What about the galaxical rotating response? What is that? Say again.
Is this galactic scale effect on rotation curves like frame dragging? It's a question from George.
I cannot make the last words you said. Is what? Like what?
Frame dragging. Let me post the question on the chat again.
Okay.
It's from George.
Okay, let me go back to those chat so that I can read those myself. Okay, frame dragging. Okay. I would not use the frame dragging to describe it. The effect from galactic rotation curves, it is like, John's unified field theory premise is space itself constantly moving at light speed. It is a medium. It has density and speed. Those two are space intrinsic properties. So and also it moves at a spiral pattern. So space moves at light speed outward from an object in cylindrical spiral motion. So when that spiral moves, the further from an observer that spiral expand actually, the effect become larger and larger. That's why when we're talking about galactic rotation that is far, far away from us, that motion, the space motion itself, the response become visible, become significant. That is galactic scale effect on rotation curves from John's unified field theory point of view. So no, we don't use it. Yeah, not a frame dragging. What was the name of the original author? Around, okay. Slide 4. Slide 4. Okay, let me go back there. Oh, yeah. So that unified field theory you are talking about, his name is Zhang Xiangqian. I also has a reference to his paper, I believe, on the last slide. Oh no, it doesn't have his. I will add that to it. But any of the links on this last slide list John's unified field theory as a reference. Yeah. Zhu Benjiang's paper is the theory of a spatial motion. Yeah, this all the papers referenced John's unified field theory. Yeah, spiral pattern is natural to the geometry and dynamics of space. Yes, that's our understanding. Yeah, that Paul posted unifiedfield.info. That website is John's official website for his unified field theory.
Yeah, I just Google search online. Electric universe theory, EU theories, is an alternative non-mainstream cosmology proposing that electromagnetism rather than gravity is the dominant force shaping the universe. I think it's a different topic.
Yeah, I guess it is. I guess the point is we are not satisfied with the mainstream explanation of the nature. So we're trying to find a better explanation of the universe and everything in it. So I guess that electric universe theory is another attempt.
Lynn, can I ask you a question,
please?
Sure, yeah.
Yeah, thank you for your presentation. It's very interesting. When I was looking at your slides, you're talking about that constant K and the density, and I was wonder both equations that you present of K and rho density or mu, I cannot extract the speed of light independently from those equations, or I could not drive the speed of light from those equations. Unlike the Maxwell equations, is simple. You can extract for known constants of permittivity and constant permeability. You can derive the speed of light. From your equations, I don't see how do you drive unless if you connect those equations to the Maxwell equations. But for the theory to have its own how to say uniqueness, should be able to drive its own speed of light. So you could say, yes, yeah, this theory is valid. We can drive speed of light independently from the well-established equations of Maxwell or and so on. That's my first point. The second point, calling it a unified field theory, I could not see that the theory is able to answer the fundamental questions of physics, the unification of general relativity and quantum mechanics, and also when you talk about large systems, cosmic systems like galaxies and so on, the theory doesn't appear also to answer the question of the Hubble constant, which the cosmologists are having difficulties to explain this variation in the Hubble constant. So it appears that the theory hasn't managed to answer all these fundamental questions.
Okay. Yeah. I heard you, and I answered them. About the speed of light. In this, in John's theory, the premise is very, very simple. It is space is constantly moving at light speed in spiral pattern. That's it. So light speed is within his premise. It is not derived from any other. It is the same as its density constant. Anything else actually derived from density and the speed of light. So that is the first question answer. And the second, yeah, I can understand. Of course, I didn't mention how that unified field theory unifies, but that is if you go to that website, unifiedfield.info, it explains articles, papers on that website explains how this unified field theory unifies all forces. Yeah, that is not covered in this talk, but if you are interested, you can read, and it is very convincing to me.
What about the last question about the Hubble constant? This expansion of the universe. Do you answer this question too?
Yeah, those questions, they are that Huang Binggang, the third paper in the links, Huang Binggang, he has answered all those questions in his papers. Those details I'm not familiar with, but Huang has answers for how those established equations are derived. He has a very detailed mathematical derivation in his paper.
Thank you.
Yeah, I'll add more links for Huang Binggang so that you can go and anybody interested could go look how he mathematically developed the unified field theory.
I get a question from Ron. If space-time is moving in a spiral, it suggests an axis of rotation and origin and destination. Is any of this explained?
Oh, yeah. Yes, that is not in my paper, obviously, but that is very well explained in John's unified field theory itself, and also Huang Bingang's papers. Huang Bingang's paper, okay, Zhang's original unified field theory only gives a very basic structure that Huang Bingang mathematically developed it. So for that axis, yes, I can explain a little bit. Yeah, three axes. They are talking about three axes. One represent they often use z-axis to present it as a radial axis, represent gravity, how mass responds to this spiral. That appears gravitational on radial axis. And there's another axis called axial. Axial is a rotation axis. It represents electromagnetic. So each 360-degree rotation completes as one action. That is also explains why in electromagnetic, it has steps. It is not a continuous motion. It is discrete motion. And another axis, the third axis, is a tangential axis. It it actually mainly represents. Let me think. Mainly represents fields. So radial represents gravitational. The axial axis represents electromagnetic rotation, and the tangential axis represents those fields, energy.
I think I saw a question on YouTube earlier. Vertex, spiral, scalable movement, just like I think we see a tornado spinning, hurricane spinning, whirlpool spinning, galaxy spinning, all the same motion.
Yeah.
So if scale them out, the universe, wouldn't it also be moving in the same way? The planet spinning around our sun, also the same movement.
Yeah, exactly. If you observe the nature, yeah, spiral motion is everywhere. Yeah, the quantum actually is not limited to quantum world. It is actually universal. The reason we do not see those quantum effects everywhere else because it's just hidden. It's phased out. It's like the Earth we thought it's flat because compared to Earth, we stand on it. Earth is too large for us to realize it is round. They are the same thing. We do not see quantum effects everywhere because it is phased out at our local scale.
Another question from the same person on YouTube, could it all be a Toronto shape the universe?
Yeah. Okay, in Young's unified field theory, the universe doesn't have a shape on its own. It's a space is I don't think it has an edge to the universe in his theory. It is just space itself moves in spiral motion, and then if we observe anything in water ripple, a ball, if you throw it, the galaxy all orbits, everything, if you observe, it represents a kind of a circular, there's a spiral shape. But I would not say the universe has a shape of some kind. But the space itself, it's moving in spiral.
So far, that's all the question that I see. Paul got a comment like a everlasting flow of water with no container.
Okay, yeah, that's a good way to describe it.
Can I ask another question? I'm still finding it difficult to understanding not only this theory, but in general, this question of ontology and the instrumental physics or mathematical physics. It's still puzzling me. Early on during your presentation, first slides, you start describing the space-time as a medium, but you said that this medium is not energy, and when you say it's not energy,
It's not what?
it's not just geometry. This is a difficult question to understand, point to understand, because if something is rotating, in spiral form, whatever form of rotation, it would imply some driving force, something drives it to drive this movement or this rotation, and that thing that to drive it may require or imply some sort of energy. So if there is no energy there, how this thing just spiraling there. So it implies the fact that is rotating itself is a kind of form of energy, isn't it?
Okay, I think I understand what your question is. Okay, so it's like a kitchen and egg, which is first. Yeah, energy from this unified field theory point of view, energy is generated by the motion of space. The premise is space is in motion. So there's since it is a premise, motion itself is included in the premise, like an axiom. Then to understand everything else, this of his framework, we need to accept this premise first, and then everything else will flow easily.
You're
I mean,
implying that the Big Bang theory is not correct.
okay, if you do not think it is correct, then you,
I'm asking you about based on this theory.
oh, okay, you ask me. I
Yeah.
definitely believe it is correct. That's why I've been working, reading, and trying to bridge it with established physics. But I understand it doesn't mean what my belief is correct. But I think this is a best theory in the sense that I think it makes most sense, more sense than any established theory that can explain things like dark matter, for example.
Okay, thanks.
Yeah. Yeah, the reality is the current physics, there are many problems with it. Even physicists know that. They don't talk about it. Just like previously, prior to the quantum physics, everybody was privately murmuring, um, but nobody spoke loudly. Currently, we are in this situation again. Physicists know something is not complete in current physics, but just like the space itself, everybody uses it. Space itself is very active in modern physics, but nobody questions it, what it is.
I got a next question on the YouTube. How can gravity hold the shape of galactic highways we see now, connecting galaxies together?
Oh, okay. Yeah, that is the okay. My understanding that the spiral motion, well, from the it requires observer, that's for certain. So we are observers, and then those galactic highways are very far away from us, and with a very enormous distance from us to the destination. Those enormous space, according to the theory, it is not empty. It is moving at light speed. And the field it generates become more and more bigger and bigger as it travels further and further from us. When it reaches the destination, that the question actually is created through frequency. Yes. That's correct. It is it is created through frequency. I think that is correct. Mm-hmm. Yeah. Yeah, it has its own re- rhythm. Yes.
There's another person saying, to me, the electric universe theory makes sense. Everything falls into place. It's very interesting.
Yeah, it's possible. I mean, yeah, it's possible. I do not know exactly how that theory describes the universe, but yeah, it's possible.
Yeah, there's a small request from Paul. He wants you to stop sharing your screen so that he can see the presenter. Yeah,
Oh, how do I do that? Let me
stop
see.
sharing the screen. Yeah.
Oh, okay. Stop. Okay.
But is there any discussion or questions? So no more questions.
Okay, then, yeah, today's talk is simple. It's but it is quite fundamental, and
How does this theory sees the universe expansion? Will it end, or is going to be continuously expanding, or is kind of cyclic universe?
and the unified field theory itself doesn't indicate any ending.
So according to this theory, the universe will stay perpetually like it is now. Oh, it's gonna end. It doesn't say anything about the end, or
No, it doesn't mention that.
continuously, or to be as it is to infinity.
It doesn't mention any of that. Yeah. But the author of that theory himself, he has many philosophical thoughts about the universe besides his theory. That part is quite interesting as well. That's a totally different topic. So if you are interested, you could go to that unified field.info to look at those publications. He has a novel, sci-fi novel, if you want to call it. In that novel, Watch Through Planet Gorka. In that novel, he expressed his philosophic, his thoughts on many aspects. Yeah, John.
Yeah, go ahead. Yeah.
The founder of the theory, John himself, currently actually, he's like he's more like a philosopher than a physicist. Other people are working on his theory, like Huang Binggang and some others. But John himself, he's more like a philosopher now.
I got a comment from Paul. He said Doppler effect may answer this. 。
Okay. 。
And the person who asked those questions on YouTube, he said, thank you so much.
Thank you for listening.
So are there more questions? If no more question, we can finish. And Lynn, thank you again for coming. If you have more topics, you're welcome to come back for more
Okay,
topics. And
thank you.
next week, we'll have Terry, not next week, in 2 weeks, we'll have Terry Bollinger. And the registration form is on chat.
Okay, yeah. I'll try to attend more sessions. Yeah.
So thank you again.
Thank you. You're the
See you in
best. Yeah. Okay, bye.